Max Planck's groundbreaking idea emerged in 1900, a year that would mark a significant turning point in the field of physics. At the time, classical physics, dominated by figures such as Isaac Newton and James Clerk Maxwell, was the prevailing framework for understanding the laws of nature. It had successfully explained much of the behavior of physical systems, from celestial mechanics to electromagnetism. However, by the late 19th century, scientists were encountering anomalies in how energy was emitted and absorbed by objects at microscopic scales. These were known as the black-body radiation problem, and they posed a serious challenge to the classical physics of the time. It was during this period of intense scientific inquiry and confusion that Max Planck, largely unknown to the world at the time, would introduce an idea that would completely alter the course of scientific history. The black-body radiation problem was not a trivial matter. A black body is an idealized, physical object that absorbs all radiation that falls on it, reflecting none, and it emits radiation based on its temperature. Classical theories, particularly those proposed by Rayleigh and Jeans, predicted that a black body would radiate an infinite amount of energy at shorter wavelengths, which was clearly not the case in reality. This so-called ultraviolet catastrophe was a direct contradiction of experimental observations. According to classical physics, the energy radiated by a black body would keep increasing as the wavelength decreased, but experiments showed that energy output actually dropped after a certain point, which classical theories could not explain. The issue was pressing, and Planck, at the time a professor of theoretical physics at the University of Berlin, was tasked with finding a solution. Like many of his contemporaries, Planck was deeply committed to the principles of classical physics, but the failure of these established theories to explain black body radiation left him with no choice but to venture into new territory. Planck's intellectual journey began with the work of previous physicists. He took into account the results of scientists like Kirchhoff, who had formulated the concept of radiation equilibrium, and Boltzmann, who had laid down some early ideas regarding entropy and statistical mechanics. Planck was well versed in these concepts, and it was through this background that he began to formulate his own approach. Planck's approach was both radical and methodical. He knew that, to explain the behavior of black body radiation, he would need to find a new way to describe how energy was emitted and absorbed at the microscopic level. At the heart of his theory was a key insight. Energy was not a continuous flow, but rather came in discrete, quantized amounts. This was an idea that contradicted the classical understanding of energy as a smooth, continuous variable. Energy could not be divided into arbitrarily small amounts, as classical physics suggested. Instead, it came in small packets, or quanta, each with a specific amount of energy determined by the frequency of the radiation. To make this idea mathematically feasible, Planck introduced a formula that would describe the energy of these quanta. This formula was based on the relationship equals E equals h ni u, where Ne is the energy of the radiation. H is a new constant that Planck introduced, now known as Planck's constant, and .nu is the frequency of the radiation. The key to this equation was the introduction of the constant .h, a fundamental number that, Planck suggested, could only be arrived at by the quantization of energy. This new approach allowed Planck to correctly predict the spectrum of black body radiation, something that classical physics had failed to do. At first, Planck himself was not fully comfortable with the implications of his discovery. He had been raised in the tradition of classical physics, and the idea that energy came in discrete units rather than a continuous flow was a difficult concept to accept. Planck initially presented his theory not as a complete overhaul of physics, but rather as a mathematical trick to make sense of the experimental data. He did not openly suggest that energy was fundamentally quantized, but he used this approach because it worked to explain the observed results. However, as time went on, it became evident that Planck's formula was more than just a mathematical tool. It was a window into the structure of the universe itself. The acceptance of this idea would lead to the birth of quantum theory, a new branch of physics that would revolutionize the way we understood the nature of reality. For many in the scientific community, Planck's theory was a bold but speculative idea that did not immediately garner widespread acceptance. Even though his formula worked perfectly for explaining black-body radiation, the notion of energy, quanta was viewed with skepticism by many physicists. It was difficult for scientists to let go of the idea that energy was continuous, and they struggled to accept that the laws of nature might be governed by such a fundamentally strange and counterintuitive principle. The scientific world had already grown accustomed to the smooth and predictable laws of classical mechanics and electromagnetism, and the idea that nature operated in discrete steps was, to say the least, unsettling. It wasn't until the work of Albert Einstein in 1905 that the full implications of Planck's idea began to be understood. Einstein's work on the photoelectric effect, which demonstrated that light could also be thought of as discrete packets of energy, or photons, brought Planck's theory into the mainstream. Einstein's explanation of the photoelectric effect provided experimental evidence for the quantization of energy and helped convince the scientific community that Planck's idea was more than just a mathematical convenience. It was a fundamental feature of the physical world. The implications of Planck's theory extended far beyond black-body radiation. His work laid the groundwork for the development of quantum mechanics, a theory that would go on to explain the behavior of particles at the atomic and subatomic levels. Quantum mechanics would eventually become one of the most successful and accurate theories in the history of science, providing explanations for phenomena that classical physics could not even begin to address, such as the behavior of electrons in atoms, the stability of atoms themselves, and the strange behavior of particles in the quantum realm. As the 20th century progressed, the ideas that Planck had introduced began to permeate the entire field of physics. The concept of quantized energy was expanded upon by other physicists like Niels Bohr, who applied it to explain the structure of atoms, and Werner Heisenberg, who formulated the uncertainty principle. These developments culminated in the creation of quantum mechanics, a theory that would be refined by many brilliant minds, including Erwin Schrödinger, Paul Dirac, and others. The advent of quantum mechanics fundamentally changed how scientists viewed the universe, opening up new fields of research and leading to innovations in technology that have had profound impacts on our daily lives. Planck's work was not only groundbreaking because it introduced the idea of quantization, but also because it marked the end of an era in which classical physics held sway over our understanding of nature. Planck had shown that the universe was not as continuous and deterministic as classical physics had led us to believe. Instead, at its most fundamental level, reality was discrete, and the laws of nature were governed by probability and uncertainty. This revelation would lead to the rise of a new physics that embraced uncertainty and probabilistic events as key features of the universe. Today, Max Planck is regarded as one of the founders of quantum theory, and his contributions to physics are considered among the most important in the history of science. His introduction of Planck's constant and his theory of quantized energy set the stage for the quantum revolution, which would lead to the development of technologies such as lasers, transistors, and modern computing. Without Planck's bold leap into the unknown, the technological advancements of the 20th and 21st centuries would have been impossible. As Max Planck's ideas began to percolate through the scientific community, the initial skepticism began to give way to understanding, albeit slowly. The work he had done on black-body radiation was no longer merely a solution to a specific experimental anomaly. It had become a cornerstone for an entirely new way of thinking about the natural world. But the transition from classical physics to quantum theory was not immediate, nor was it without resistance. Many of the world's top physicists remained attached to the belief in a continuous, deterministic universe. They struggled to let go of the old paradigms that had served them so well for centuries. The first breakthrough came in 1905, when Albert Einstein, the young physicist who would go on to change the world with his theories of relativity, applied the concept of energy quanta to explain the photoelectric effect. In doing so, Einstein showed that light was not simply a continuous wave, as had been believed for centuries, but also had a particle-like quality. This was a profound realization, and it was a direct consequence of Planck's theory. Einstein's work on the photoelectric effect demonstrated that light, like energy in Planck's model, came in discrete packets, or quanta, and that these packets were responsible for the emission of electrons from metal surfaces when light was shined on them. Einstein's theory was experimentally verified in the years that followed, giving strong support to the notion of quantization and cementing Planck's place in history. However, even as these breakthroughs began to pile up, the wider implications of Planck's ideas were still not fully understood. In many ways, Planck himself was hesitant to embrace the full scope of his discoveries. He continued to hold on to the classical notion that physics should remain deterministic and continuous. In his own mind, Planck's quantization was merely a mathematical trick, a means of explaining the data, rather than a deep, ontological feature of the universe. He was reluctant to abandon the well-established ideas of classical physics, and it took years before he truly came to terms with the fact that his work had fundamentally altered the way that nature operated at its most fundamental level. As the years passed, a new generation of physicists began to grasp the implications of Planck's work more fully. In particular, the work of Niels Bohr in the early 20th century would expand on Planck's quantization idea and apply it to the structure of the atom. Bohr proposed that electrons within an atom could only occupy certain discrete energy levels, and that they would not spiral into the nucleus, as classical physics had predicted. This was another victory for Planck's theory, as it showed that the very structure of atoms was determined by quantum rules rather than classical ones. Bohr's model was not perfect, but it introduced the notion of quantized orbits, a direct extension of Planck's work. The breakthrough moments continued to arrive in rapid succession. As physicists began to probe the subatomic world, they discovered more phenomena that could only be explained by the principles of quantum mechanics. The idea that energy was quantized led to the recognition that matter itself must have a similar discrete structure. This idea was first hinted at by Planck, but it was made explicit by Werner Heisenberg in his formulation of the uncertainty principle, which stated that certain pairs of physical properties, such as position and momentum, could not be simultaneously measured with arbitrary precision. Heisenberg's uncertainty principle was not merely a mathematical oddity, it was a fundamental property of nature itself, and it revealed that the world at the atomic and subatomic level was inherently uncertain and probabilistic rather than deterministic. As quantum mechanics began to evolve, physicists like Erwin Schrödinger, Paul Dirac, and others refined the theory, developing new ways to describe particles and their interactions. Schrödinger's wave equation, which described the probability distribution of particles, and Dirac's relativistic quantum theory, which combined quantum mechanics with special relativity, represented some of the major advances in the field. These ideas would eventually lead to the development of the Standard Model of particle physics, which describes the fundamental particles and forces that make up the universe. The discoveries of the 20th century, all of which were grounded in Planck's original insight, have allowed us to probe the nature of matter and energy with unprecedented precision. As the field of quantum mechanics advanced, So too did the technological applications of Planck's work. The quantization of energy, which was first demonstrated in Planck's formula for black-body radiation, became the basis for technologies like lasers, semiconductors, and transistors. These devices, which are now essential components of modern electronics, owe their existence to Planck's theory. Without his work, we would not have the computers, smartphones, or other electronic devices that we rely on every day. The concept of quantized energy also paved the way for the development of quantum computing, a rapidly growing field that promises to revolutionize the way we process information. Quantum computers, which leverage the principles of superposition, entanglement, are still in the early stages of development, but they represent a potential breakthrough that could change the world in ways we can't yet fully imagine. Moreover, Planck's work set the stage for a rethinking of the entire philosophy of science. Before quantum mechanics, the scientific community largely adhered to the idea of determinism, that the universe operated in a predictable cause and effect manner. Planck's introduction of the quantum revolution, however, shattered this belief. The quantum world, where probabilities reign and certainty is elusive, forced scientists to abandon the idea that the universe could be completely understood through deterministic laws. This realization gave rise to new philosophical questions about the nature of reality, observation, and the limits of human knowledge. Many philosophers, like Werner Heisenberg and Niels Bohr, wrestled with the implications of quantum mechanics and their ideas on the role of the observer in the quantum world would profoundly impact not only physics but also our broader understanding of the universe. Max Planck's contributions to science are immense, and his legacy is far-reaching. His work marked the dawn of the quantum era, setting the stage for the breakthroughs that would follow. Planck's ability to think beyond the constraints of classical physics and to embrace the radical notion of quantization was instrumental in creating the foundation for the modern understanding of physics. His work helped reveal a universe that was far more mysterious and complex than anyone had imagined, one governed by probabilities, uncertainties, and discrete quantities. Today, the technology that drives our world is built upon the principles that Max Planck first proposed over a century ago. The very structure of the atoms that make up our world, the behavior of light and radiation, and the possibilities of new technologies like quantum computing all have their roots in Planck's crazy idea. In this sense, Max Planck's work was not just an abstract scientific discovery, but a profound shift in how humanity interacts with the world. His theory opened doors that were previously closed and forever changed the trajectory of modern science. In conclusion, the crazy idea that Max Planck proposed in 1900 wasn't just a solution to a scientific problem. It was a radical shift in our understanding of the universe. Through his groundbreaking theory of quantized energy, Planck unlocked a new realm of physics that would lead to the development of quantum mechanics, revolutionizing science and technology in ways that continue to unfold today. Max Planck's legacy is a testament to the power of bold ideas and the willingness to challenge established norms in pursuit of greater understanding. His work continues to inspire new generations of scientists, thinkers, and innovators, ensuring that his crazy idea will remain a defining moment in the history of human knowledge for generations to come. Max Planck's introduction of a new constant, later known as Planck's constant, h, marked a pivotal shift in the realm of physics. This constant would become one of the most fundamental constants in nature, deeply interwoven with the structure of quantum mechanics and the theory of relativity. For decades, the concept of quantized energy had been elusive, viewed with skepticism by many within the scientific community. The classical approach assumed energy could be transferred or emitted in a continuous fashion, but Planck's radical idea was that energy existed in discrete packets. His constant, h, served as the bridge that connected classical ideas with the emerging quantum world. In understanding the significance of Planck's constant, we need to understand its place in the larger puzzle that was physics at the time. The late 19th and early 20th centuries represented an era of turbulence and transition in physics. Classical mechanics, as codified by Isaac Newton and expanded by figures such as James Clerk Maxwell and Ludwig Boltzmann, had dominated for over 2 centuries. The laws of motion, thermodynamics, and electromagnetism explained a vast array of phenomena, from the orbits of planets to the behavior of light. However, when it came to understanding atomic and subatomic phenomena, the classical framework began to fail. Planck's contribution came when he was tasked with solving one of the most perplexing problems of the time, the problem of black body radiation. The classical theory, known as the Rayleigh-Jeans law, predicted that a black body, an idealized object that absorbs all incoming radiation and emits radiation at different wavelengths based on its temperature, would radiate infinite energy as the wavelength approached zero, a contradiction to experimental observations. The solution to this paradox lay in quantizing the energy emitted or absorbed by a body. Planck introduced a constant into his formula for the first time in 1900, establishing the relationship equals est, E equals TNIU, where E is the energy of the radiation, est, E is Planck's constant, and T Ni-U is the frequency of the radiation. This simple, elegant formula did not just solve the problem of blackbody radiation. It also revealed a deeper truth about the nature of energy and light itself. At first, Planck himself was reluctant to accept the full implications of his constant. To him, it was merely a mathematical trick, a tool to make sense of the experimental data. Yet, as the formula proved successful in explaining the radiation spectrum, and as more experiments came to support it, the deeper significance of Planck's constant became clear. It was no longer just a numerical value in a formula. It was a reflection of the discrete nature of energy. Planck's constant marked the first step in an entirely new direction for physics, the birth of quantum theory. This concept of quantization was radically different from the classical view of energy as a smooth, continuous variable. For centuries, energy had been understood to flow in an uninterrupted fashion, a constant in motion. The very idea that energy could only be exchanged in discrete, indivisible packets challenged long-held assumptions about the nature of reality. It suggested that the universe at its most fundamental level might not be a seamless, predictable continuum, but a collection of tiny, quantized units of energy. The introduction of Planck's constant was the key that unlocked this understanding. Planck's constant did more than merely explain black body radiation. It laid the groundwork for the development of quantum mechanics. The constant's discovery opened up new avenues of exploration in the behavior of light and matter. For instance, Albert Einstein would soon apply Planck's quantization concept to the photoelectric effect, demonstrating that light itself was quantized and composed of discrete packets of energy known as photons. Later, other developments in quantum mechanics, such as Niels Bohr's model of the atom, Werner Heisenberg's uncertainty principle, and Erwin Schrödinger's wave mechanics, would all build upon Planck's work. Planck's constant also had immediate practical implications. Its role in quantum mechanics allowed for the development of new technologies. Without the understanding of quantization that Planck's constant enabled, the advancements in electronics, such as the development of semiconductors, lasers, and transistors, would not have been possible. The discovery of Planck's constant marked the dawn of the technological revolution that would reshape the world in the 20th century, from computers to telecommunications to the medical field. The recognition of Planck's constant was not instantaneous. It took time for the broader scientific community to accept the implications of quantum theory. Many physicists, including Planck himself, were hesitant to fully embrace the quantum perspective. Classical mechanics had been an immensely successful theory in its own right, and the shift to a new, radically different framework was not an easy one to make. It was only with the cumulative efforts of Planck's successors, such as Einstein, Bohr, Heisenberg, and Schrödinger, that quantum mechanics became established as the dominant theory in physics. In the years following the introduction of Planck's constant, the development of quantum mechanics would reshape not only the world of physics, but also our understanding of the universe itself. The principles of quantum mechanics revealed that, at the atomic and subatomic levels, the universe behaves in ways that are fundamentally different from what we experience in our everyday lives. At these small scales, particles exist in a state of superposition, can be entangled with one another, and follow probabilistic rather than deterministic paths. The uncertainty principle, the idea that we cannot simultaneously know the exact position and momentum of a particle, fundamentally altered our conception of reality. Quantum mechanics also led to the development of entirely new fields of science and technology. In chemistry, it provided a framework for understanding the behavior of atoms and molecules, which led to the development of fields like molecular biology and materials science. In computing, quantum theory promised the possibility of a new kind of computer that could harness the strange behavior of quantum bits, or qubits, to perform calculations far more quickly than traditional computers. The introduction of Planck's constant thus represented not just an intellectual breakthrough, but a gateway to a host of technological advancements that would transform modern society. But perhaps the most significant implication of Planck's constant was its role in challenging the deterministic worldview that had dominated scientific thought for centuries. Classical mechanics, with its emphasis on cause and effect, had created an image of a universe that operated like a vast machine, each part functioning according to predictable laws. The introduction of quantization and the uncertainty principle that would follow shattered this image. It revealed a universe that, at its most fundamental level, was governed by probabilities, uncertainty, and a deep, intrinsic randomness. This realization was both liberating and unsettling, as it suggested that not everything in the universe could be known or predicted with certainty. As the years went by, the full implications of Planck's constant continued to unfold. In 1927, Heisenberg introduced the uncertainty principle, which stated that we cannot simultaneously measure both the position and momentum of a particle with arbitrary precision. This principle directly followed from Planck's idea of quantized energy and showed that nature itself imposes fundamental limits on what can be known about a system. In essence, the act of measuring one property of a system interferes with the measurement of another. This was a stark contrast to the classical view, where all properties could in theory be measured and known with perfect accuracy. Planck's constant also had a profound effect on the philosophy of science. It raised deep questions about the nature of observation and reality. If our measurements are inherently uncertain, and if the very act of measurement affects the system, what does that mean for our understanding of the universe? Does reality exist independent of our observations, or is it shaped by the act of measurement? These questions led to intense philosophical debates within the scientific community, particularly between the proponents of the Copenhagen interpretation, led by Niels Bohr, and those who sought a more deterministic, realist interpretation of quantum mechanics. By the mid-20th century, quantum mechanics had become the dominant theory in physics, explaining phenomena that classical physics could not even begin to address. Quantum mechanics became the foundation for much of modern technology, including lasers, semiconductors, and computers. The advent of quantum computing, still in its infancy, promises to take us even further into uncharted territory, potentially solving problems that are currently intractable with classical computers. In conclusion, the introduction of Planck's constant by Max Planck was a defining moment in the history of science. It marked the beginning of the quantum revolution, which would reshape our understanding of the universe at its most fundamental level. It revealed that energy is quantized, that the universe operates in discrete units, and that the universe is probabilistic rather than deterministic. Planck's constant is more than just a number, it is a symbol of the radical shift in our understanding of nature, and its implications continue to influence science and technology to this day. In the early 20th century, when Planck introduced the idea of quantized energy, few could have predicted how transformative this concept would be. Planck's constant, and the notion that energy was discrete instead of continuous, was the first stepping stone toward the creation of a new theory that would soon overthrow centuries of classical physics, quantum mechanics. This theory would not only describe the behavior of subatomic particles, but also lead to a whole new way of understanding the universe, one that rejected determinism in favor of uncertainty, probability, and waves of energy that behaved both like particles and waves. Quantum mechanics emerged as a unified theory only after decades of intense development, as many of the brightest minds in physics worked to understand the bizarre phenomena of the atomic and subatomic worlds. As we explore this evolution, it's essential to focus on the foundational elements that Planck's work laid out, particularly his discovery. That energy is quantized, leading to a conceptual shift that would become one of the most significant breakthroughs in human history. The birth of quantum mechanics is rooted in several key moments, all of which can be traced back to Planck's radical insight. As we transition from classical physics, which viewed the world in terms of predictable, deterministic laws, to quantum mechanics, we move toward a probabilistic, uncertain universe at the atomic scale. This was a sharp departure from the ideas of Newtonian physics, where the world was understood to function like a clock, with everything moving in clear, predictable paths. The implications of quantum mechanics, which stemmed from Planck's initial ideas, would dramatically change our understanding of time, space, and reality itself. The first major application of Planck's ideas came when Albert Einstein used the concept of quantized energy to explain the photoelectric effect in 1905. Einstein showed that light was not only a wave, as had been understood since the work of Thomas Young and James Clerk Maxwell, but also had particle-like properties. The energy of light could only be absorbed or emitted in discrete amounts, which he called photons. This notion was revolutionary because it contradicted the traditional wave theory of light, which could not explain how light interacted with matter in certain situations. Einstein's work on the photoelectric effect validated Planck's quantization of energy, marking a turning point in the understanding of both light and energy. Building on these developments, other physicists began to apply the idea of quantization to other aspects of matter. Niels Bohr was the next scientist to significantly contribute to the development of quantum theory. In 1913, Bohr used Planck's quantization concept to explain the structure of the atom. At the time, the model of the atom was still based on the idea of electrons moving in orbits around a central nucleus, much like planets orbiting the Sunday. However, the classical theory couldn't explain the stability of these orbits, as it predicted that electrons should spiral into the nucleus due to the emission of radiation. Bohr resolved this by suggesting that the electrons in an atom could only occupy certain allowed orbits, each corresponding to a specific energy level. Electrons could absorb or emit energy in discrete amounts, jumping between these orbits. This model, known as the Bohr model of the atom, was based on the quantization of energy and was the first step toward understanding atomic structure in quantum terms. As quantum theory gained momentum, it became clear that the classical view of physics was inadequate for explaining the behavior of particles at very small scales. Werner Heisenberg, in 1925, formalized a key concept that would forever change our view of reality: the uncertainty principle. This principle states that it is impossible to simultaneously know both the exact position and momentum of a particle. The more precisely one of these properties is measured, the less precisely the other can be known. This was a radical departure from classical physics, which assumed that both position and momentum could be determined precisely. The uncertainty principle shattered the deterministic view of the universe, suggesting that on the quantum level, the very act of measurement disturbs the system, creating inherent uncertainty. Around the same time, Erwin Schrödinger developed his wave mechanics, which described particles not as points moving along deterministic paths, but as wave functions, mathematical descriptions of the probabilities of where a particle might be found. Schrödinger's famous equation, the Schrödinger equation, was a key development in quantum mechanics, showing how the wave function evolves over time. According to this theory, particles at the quantum level do not have definite positions or velocities. Instead, they exist as probability waves that can spread out across space, and only when measured do they collapse into a specific position. This wave-particle duality, where particles behave both as waves and particles depending on the situation, became a defining feature of quantum mechanics. As the quantum theory developed, it became clear that classical physics was no longer sufficient to explain the strange behaviors of particles at the subatomic level. The shift from a deterministic worldview, where every action has a predictable cause, to a probabilistic worldview, where uncertainty and randomness play a central role, was profound. In the quantum world, particles do not move in predictable orbits, and their properties cannot always be known with certainty. Instead, their behavior is governed by probability and wave functions, with outcomes determined by chance rather than determinism. Quantum mechanics also introduced the concept of entanglement, a phenomenon that Einstein himself called spooky action at a distance. In 1935, Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, proposed the famous EPR paradox, which sought to highlight the contradictions in quantum mechanics. The paradox posed the question of whether quantum mechanics could provide a complete description of physical reality. Their argument was based on the idea that particles could be entangled, meaning that the state of one particle would be immediately correlated with the state of another, no matter the distance between them. This suggested that particles could communicate with each other faster than the speed of light, challenging Einstein's theory of relativity. Despite Einstein's skepticism, experiments later confirmed that quantum entanglement was real, further demonstrating the strange, non-intuitive nature of quantum mechanics. As the field evolved, it became clear that quantum mechanics was not merely an abstract theory, it had practical applications that have transformed technology. The discovery of semiconductors in the 20th century was one of the first major applications of quantum mechanics, leading to the creation of transistors and modern electronic devices. Quantum mechanics also enabled the development of lasers, which have countless applications in fields ranging from telecommunications to medicine. More recently, quantum computing has emerged as a promising new frontier, leveraging the strange behavior of particles to perform computations at speeds far beyond the capabilities of classical computers. Though still in its infancy, quantum computing holds the potential to solve problems that are currently unsolvable with conventional computing methods. The journey from Planck's discovery of quantized energy to the full development of quantum mechanics illustrates a fundamental shift in our understanding of the universe. Planck's constant, the key that unlocked the quantum world, has become one of the most important constants in physics. It has allowed us to understand and predict the behavior of the smallest particles in nature, and has paved the way for technologies that have reshaped our world. Quantum mechanics has not only transformed science and technology, but has also had a profound impact on philosophy. The shift from a deterministic to a probabilistic universe raised questions about the nature of reality itself. What does it mean to observe a particle? How do our measurements affect the world around us? These questions have led to deep philosophical debates about the nature of knowledge, observation, and the limits of human understanding. In conclusion, quantum mechanics emerged from Max Planck's revolutionary insight that energy is quantized, a concept that paved the way for the development of a new physics, one that embraced uncertainty, probability, and the strange duality of light and matter. The advancements that followed, from Einstein's explanation of the photoelectric effect to Schrödinger's wave mechanics and Heisenberg's uncertainty principle, have not only redefined our understanding of the universe, but have also given rise to technologies that have transformed our world. Quantum mechanics, founded on Planck's constant, remains one of the most powerful and successful theories in science, and it continues to shape our exploration of the universe, both in the lab and in the theoretical realm. The quantum revolution is one of the most significant shifts in scientific understanding in human history. It radically altered how we perceive the universe at its most fundamental level. The revolution did not occur overnight, nor did it arise from a single individual's insight. Instead, it was the culmination of the work of many brilliant physicists, from Max Planck to Albert Einstein, Niels Bohr, and Werner Heisenberg. The collective efforts of these scientists laid the foundation for what we now call quantum mechanics, a theory that describes the behavior of matter and energy at atomic and subatomic scales. While quantum mechanics has been an overwhelmingly successful theory, it has also transformed much more than just physics. It has impacted philosophy, technology, and society at large. The roots of the quantum revolution can be traced back to Max Planck's discovery in 1900 that energy is quantized, divided into discrete packets, rather than flowing in a smooth continuum. This revelation marked the first step in a journey that would forever alter the landscape of physics. It would be another 5 years before Albert Einstein took this concept further, applying Planck's quantization idea to explain the photoelectric effect. Einstein's insight that light has both wave-like and particle-like properties gave rise to the theory of wave-particle duality, a core idea that would later form the foundation of quantum mechanics. The acceptance of quantum theory eventually led to a dramatic shift away from classical physics, where the world was perceived as a predictable and deterministic system, to one that embraced probability, uncertainty, and indeterminacy. One of the most profound shifts that quantum mechanics brought to the table was the rejection of determinism, which had reigned in physics since the days of Newton. Classical physics, especially Newtonian mechanics, was built on the assumption that the universe operated like a grand clockwork machine, where every event had a precise cause and every effect could be predicted with certainty if enough information were known. According to this view, the universe was entirely predictable and deterministic. If we knew the position and velocity of every particle in the universe, we could calculate their future movements with precision. But as scientists began probing the atomic and subatomic realms, they quickly realized that such predictability no longer held. The introduction of Heisenberg's uncertainty principle in 1927 shattered the classical belief in determinism. The uncertainty principle stated that it is impossible to know both the exact position and momentum of a particle simultaneously with absolute precision. This wasn't simply a limitation of measurement tools, it was an inherent property of nature itself. The very act of measuring one of these quantities disturbs the particle in a way that alters the other. This realization meant that, at the quantum level, the future of a system could not be predicted with absolute certainty, only probabilistically. The universe, at the quantum scale, was not a well-oiled machine, but a realm of uncertainty, governed by the probabilistic laws of quantum mechanics. As quantum mechanics took shape, it became clear that the classical deterministic model of reality was inadequate for explaining the behavior of particles at atomic and subatomic scales. The behavior of these tiny particles could no longer be described in terms of fixed trajectories or simple cause and effect relationships. Instead, quantum mechanics introduced the concept of probability waves, where particles existed in a state of superposition, meaning that they could be in multiple states at once, and only when measured did their properties collapse into a definite value. This idea was first formulated in Schrödinger's wave mechanics, which described particles as probability waves spread out across space instead of discrete particles with definite positions. This quantum leap into a world of uncertainty and probability was not easily accepted by all physicists. In fact, the new quantum theory was deeply controversial, and many of its early proponents, including Albert Einstein, struggled to fully accept its implications. Einstein famously remarked, "God does not play dice with the universe," expressing his discomfort with the inherent randomness that quantum mechanics introduced. Einstein believed that there must be some underlying, hidden variables that would restore determinism to the universe. Despite his reservations, however, even Einstein's work on the photoelectric effect helped to lay the groundwork for quantum theory. Still, the notion that events at the quantum level were governed by probability rather than certainty was a bitter pill to swallow for many in the scientific community. Quantum mechanics was not just an abstract theory, it was a practical tool that led to groundbreaking discoveries and technological advancements. The application of quantum mechanics in atomic physics was one of the earliest success stories. Niels Bohr's model of the atom, developed in 1913, was based on the idea that electrons could only occupy discrete energy levels, with the atom's stability relying on these quantized orbits. This model successfully explained the behavior of atoms and their emission spectra, something that classical models had been unable to do. Bohr's model, combined with Planck's constant, became the cornerstone of atomic theory, marking the beginning of the quantum revolution in applied physics. By the 1920 seconds and 1930 seconds, quantum mechanics was being applied to increasingly complex systems, from atomic to molecular and eventually solid-state physics. The development of quantum field theory and the standard model of particle physics was built on the foundation laid by quantum mechanics. The standard model, developed over the course of the 20th century, describes the fundamental particles and forces that make up the universe, excluding gravity. Quantum mechanics provided the mathematical framework to understand the interactions between particles such as electrons, photons, quarks, and gluons through forces like electromagnetism, the weak nuclear force, and the strong nuclear force. One of the most profound and far-reaching effects of the quantum revolution was the development of quantum technology. In the second half of the 20th century, the principles of quantum mechanics gave rise to numerous technological advancements. Semiconductors, which form the basis for modern electronics, were made possible by the understanding of quantum behavior in materials. The invention of the transistor, which revolutionized computing and telecommunications, would not have been possible without quantum mechanics. The development of lasers, which rely on quantum principles like the population inversion of energy states, transformed a wide range of industries, from telecommunications to medicine. The quantum computer, still in its early stages, holds the potential to revolutionize fields like cryptography, optimization, and artificial intelligence by leveraging the strange properties of quantum bits, or qubits, to process information in ways that classical computers cannot. Another field that benefited immensely from the quantum revolution was nuclear physics. Quantum mechanics was essential in understanding the behavior of nuclear particles and reactions. The development of nuclear energy and nuclear weapons was made possible by the discovery of fission, a quantum mechanical process that involves the splitting of atomic nuclei. The principles of quantum mechanics also underpin the understanding of nuclear fusion, the process that powers stars, and the development of technologies like nuclear magnetic resonance, NMR, which has important applications in medicine and material science. Beyond its technical applications, quantum mechanics has also deeply influenced the philosophy of science. As the theory developed, it became clear that our intuitive understanding of the world, shaped by classical physics, was no longer sufficient. Quantum mechanics suggested that the universe at the microscopic scale was radically different from what we experience in our macroscopic, everyday world. The observer effect, where the act of measuring a system can alter its state, and the wave-particle duality of light, which behaves as both a particle and a wave, challenged long-standing assumptions about the nature of reality. This led to philosophical debates about determinism versus indeterminism and the role of the observer in shaping physical reality. Quantum mechanics suggests that reality itself is not fixed, but rather exists in a state of potential until observed. This raises fundamental questions about the nature of existence, causality, and the limits of human knowledge. For some, this was a deeply unsettling thought, while for others, it was an exciting new frontier for scientific and philosophical exploration. In the context of quantum entanglement, an idea first proposed by Einstein and his colleagues in the EPR paradox, Einstein, Podolsky, and Rosen, the quantum revolution also raised questions about non-locality, the idea that particles can be instantaneously correlated with one another, no matter how far apart they are. This phenomenon seems to violate the principle of locality, which holds that objects can only be influenced by their immediate surroundings. However, experiments conducted in the late 20th century confirmed that entanglement is real, with particles behaving as if they are connected even across vast distances. The quantum revolution, though still in its early stages, has far-reaching implications for our understanding of the universe. It challenges our assumptions about the nature of reality and provides a framework for understanding phenomena that were once beyond comprehension. The implications of quantum mechanics extend far beyond physics, influencing areas as diverse as philosophy, computing, and the nature of knowledge itself. In conclusion, the quantum revolution initiated by Max Planck and expanded upon by scientists like Einstein, Bohr, Heisenberg, and Schrödinger fundamentally altered our understanding of the universe. It introduced a new worldview, one based on probability and uncertainty, and opened the door to a range of scientific advancements that have shaped the modern world. From the development of quantum technologies to the philosophical questions it raises about the nature of reality, the quantum revolution continues to inspire and challenge us to rethink the very foundations of science and existence. The quantum revolution has reshaped not only the understanding of the physical universe, but also human civilization itself. The influence of quantum mechanics stretches far beyond the confines of physics, touching nearly every aspect of modern life. The development of new technologies, the alteration of fundamental philosophical assumptions, and the expanding frontier of scientific knowledge are all direct consequences of the quantum breakthroughs that emerged in the 20th century. As we continue to explore the profound impacts of the quantum revolution, it becomes evident that quantum mechanics is the cornerstone of many of the technologies that power our modern world. One of the most prominent examples is the field of electronics. The quantum mechanical properties of materials, particularly semiconductors, form the basis of virtually every electronic device today. Transistors, invented in the mid-20th century, revolutionized the world of computing and telecommunications. The transistor, A small, solid-state device that controls the flow of electrical current is one of the foundational components of modern electronic circuits. Without an understanding of quantum mechanics and the behavior of electrons in semiconductors, transistors would not have been possible. These components form the backbone of everything, from mobile phones and computers to household appliances and advanced industrial machinery. The development of integrated circuits, which allow millions of transistors to be placed on a single microchip, further exemplifies the profound influence of quantum mechanics. This has led to the miniaturization of electronics, making computers and consumer technology more powerful and accessible. The phenomenon of quantum tunneling, where particles pass through barriers they would not be able to surmount according to classical physics, is directly involved in the operation of modern devices like flash memory and hard drives, enabling the storage and retrieval of data at unprecedented speeds. Another cornerstone of modern technology, driven by quantum principles, is the laser. Quantum mechanics explains how lasers work, based on the process of stimulated emission. In a laser, atoms or molecules are excited to a higher energy state and then undergo a transition to a lower energy state, emitting light in the process. This light is coherent, meaning it has a single wavelength and phase, which is essential for applications ranging from fiber optic communication to medical treatments like laser eye surgery and cancer therapies. Lasers are also used in barcode scanners, DVD players, and a range of other devices. Without the quantum understanding of light's behavior, such technologies would not exist. Quantum mechanics also played a critical role in the development of nuclear fission energy. The theory of quantum mechanics explains the behavior of atomic nuclei, which is fundamental in understanding nuclear fission and fusion processes that release energy from the nucleus of an atom. Nuclear fission, the splitting of heavy atomic nuclei, was harnessed to develop nuclear reactors that generate electricity. Similarly, nuclear fusion, the process that powers the sun and other stars, holds the potential to provide almost limitless, clean energy if scientists can develop the technology to control it. Quantum mechanics is indispensable in the study of nuclear reactions, as it helps explain the forces and interactions that govern atomic nuclei. While quantum mechanics has driven technological progress, its impact extends beyond the purely material to more philosophical realms. One of the most profound shifts introduced by quantum theory is the challenge it poses to determinism. In classical physics, particularly Newtonian mechanics, the universe was viewed as a deterministic system. Every event, from the motion of celestial bodies to the behavior of particles, followed a set of predetermined laws. If we knew the initial conditions of a system, its position, velocity, and forces acting upon it, we could predict its future with complete certainty. This deterministic view of the universe was deeply ingrained in scientific and philosophical thought. Quantum mechanics shattered this worldview by introducing uncertainty and probability into the equation. The Heisenberg uncertainty principle suggested that we could not simultaneously know both the exact position and momentum of a particle. More importantly, the uncertainty principle was not just a limitation of measurement tools, it was an inherent property of nature. On a fundamental level, particles did not have precise positions or velocities until they were measured. Before measurement, their properties existed in a probabilistic superposition of all possible values. This was a radical departure from the classical idea that objects have definite properties independent of observation. This new understanding of nature raised important philosophical questions about the nature of reality and the role of the observer. If particles only have definite properties when they are measured, what does that imply about the nature of reality itself? Is the universe a fixed, objective entity that exists independent of our observation, or does it depend on our consciousness to collapse the wave function and give it definite properties? These questions led to the development of several interpretations of quantum mechanics, each trying to answer the mystery of how the probabilistic wave functions of quantum particles relate to the deterministic world that we experience. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, is one of the most widely accepted views. It suggests that quantum particles exist in a superposition of all possible states until they are measured, at which point their wave function collapses into a definite state. According to this view, reality is not a static, objective entity. Instead, it is fundamentally tied to observation and measurement. This view has been the subject of much debate, particularly because it seems to suggest that the act of observing a system fundamentally alters its state. Another interpretation of quantum mechanics, called the many worlds interpretation, proposed by Hugh Everett in 1957, takes a radically different approach. Instead of suggesting that the wave function collapses upon observation, the many worlds interpretation suggests that all possible outcomes of a quantum measurement actually occur, but in separate, branching worlds. According to this interpretation, every time a quantum event occurs, the universe splits into different branches, each representing a different outcome. This interpretation removes the need for an observer to collapse the wave function, but raises its own set of questions about the nature of reality and the structure of the universe. These debates about observation and reality in quantum mechanics have led to a broader philosophical exploration of determinism versus indeterminism. Classical physics offered a deterministic view of the world, but quantum mechanics, with its probabilistic nature, introduced a sense of randomness and uncertainty. This led some philosophers to question whether the universe is fundamentally unpredictable and chaotic, or whether there is some underlying order or hidden variables that we simply do not yet understand. The questions raised by quantum mechanics are not only philosophical, but also deeply tied to the future of scientific inquiry, as they challenge our ability to fully understand and control the universe. The philosophical implications of quantum mechanics extend beyond the purely scientific. Quantum mechanics has contributed to epistemology, the study of knowledge, by challenging the very notion of what can be known about the world. If measurement affects the state of a system, can we ever truly know the objective reality of the universe, or are we only interacting with an approximation of it? These questions have implications for everything from the philosophy of science to our understanding of consciousness itself. Quantum mechanics has even influenced fields such as psychology and the study of consciousness, with some theorists proposing that quantum processes may play a role in human cognition and the emergence of consciousness. The quantum revolution also had a profound effect on the global economy. As quantum technologies became more refined, they opened up new industries and markets. Quantum computing, for example, promises to solve problems that are currently intractable for classical computers. Problems like optimization, cryptography, and simulating molecular behavior could become solvable in ways that were previously unimaginable. The development of quantum cryptography, which uses quantum principles to create secure communication systems, has already begun to change the landscape of cybersecurity, offering protection against attacks that could break current encryption methods. In addition to quantum computing, quantum sensors are poised to revolutionize fields such as medical imaging, navigation, and environmental monitoring. Quantum sensors take advantage of quantum mechanical phenomena, like superposition and entanglement, to achieve measurement precision far beyond classical limits. For example, quantum sensors could enable ultra-sensitive measurements of gravitational waves or provide more accurate and stable clocks, which are essential for technologies like GPS. The future of quantum technologies is still unfolding. As researchers continue to explore the strange behavior of quantum particles, new applications and breakthroughs are likely to emerge, shaping the next generation of scientific advancements. Quantum mechanics, once a theoretical abstraction, has transformed into a powerful tool with practical, real-world applications that will continue to affect every facet of human life for decades to come. In conclusion, the quantum revolution initiated by Max Planck and developed by physicists such as Albert Einstein, Niels Bohr, and Heisenberg fundamentally reshaped our understanding of the universe. It led to the development of technologies that have transformed society, and it introduced philosophical questions that continue to challenge our deepest assumptions about reality. From semiconductors and lasers to quantum computing and philosophy, the quantum revolution has far-reaching implications that extend well beyond physics. As we continue to explore the strange and exciting world of quantum mechanics, we can expect even greater innovations that will shape the future of science, technology, and human knowledge. The emergence of Planck's constant and the subsequent development of quantum mechanics created profound changes, not just within the realm of physics, but across multiple domains of science and technology. The quantum revolution beginning with Max Planck's work in 1900, laid the foundation for understanding the behavior of matter and energy at atomic and subatomic scales, opening up new avenues for research and technological advancement. Max Planck's insight that energy is emitted in discrete amounts, not continuously, sparked a seismic shift in how scientists viewed the universe. Before Planck, the prevailing view was that energy could be measured in a continuous spectrum, much like a smooth, uninterrupted flow. However, Planck's discovery of quantization, where energy is delivered in tiny, indivisible packets called quanta, offered an entirely new framework. This concept challenged the classical understanding of physics and, over time, led to the creation of quantum mechanics. The most immediate impact of Planck's constant came in the form of the photoelectric effect, which Albert Einstein used to demonstrate that light itself behaves like both a particle and a wave. This revelation led to the birth of the wave-particle duality of light, one of the cornerstones of quantum theory. Einstein's application of Planck's quantization idea showed that light is not just a continuous wave, as previously thought, but also exists in discrete units called photons. This insight not only explained the photoelectric effect, but also paved the way for further developments in quantum mechanics, influencing subsequent advancements in both theoretical and experimental physics. The next major leap in the quantum revolution came with Niels Bohr's model of the atom By incorporating Planck's idea of quantization, Bohr was able to explain why electrons orbit the nucleus in specific, discrete energy levels, rather than continuously. This model, which applied the quantization of energy to the structure of atoms, was instrumental in understanding atomic behavior and was a precursor to later developments in quantum mechanics. Bohr's model, although not entirely accurate, provided the first quantum explanation for atomic stability and emission spectra, which had long been a mystery to scientists. As quantum mechanics continued to evolve, so too did its philosophical implications. The notion of uncertainty became central to quantum theory, particularly with Werner Heisenberg's uncertainty principle. This principle states that certain pairs of properties, such as position and momentum, cannot be simultaneously measured with infinite precision. This introduced an element of fundamental unpredictability at the quantum level, marking a stark contrast to the deterministic view that classical physics had long upheld. The uncertainty principle challenged our understanding of the universe, suggesting that on the most fundamental level, reality is governed by probabilities rather than certainties. This shift led to debates about the nature of reality, itself, whether the universe operates as a predictable machine or whether it is inherently uncertain and probabilistic. The application of quantum mechanics transcended theoretical physics, fueling a series of technological innovations, that have transformed the modern world. Quantum mechanics is the basis for semiconductors, and transistors, essential components of modern electronics. The invention of the laser which relies on the principles of quantum mechanics, revolutionized everything from communication systems to medical technology. Quantum computing. Promises to push the boundaries even further, offering solutions to complex problems that are beyond the reach of classical computers. In addition to technology, quantum mechanics has also shaped the philosophy of science. The probabilistic nature of quantum mechanics led to new perspectives on determinism, and free will, creating a framework where outcomes are not predetermined, and the act of observation plays a significant role in shaping the state of the system being observed. This quantum framework has influenced a wide range of disciplines, from the development of new technologies to the study of consciousness and the fundamental nature of existence. The quantum revolution, through its many scientific, technological, and philosophical contributions, continues to shape the trajectory of human knowledge in profound and often unexpected ways. In conclusion, the quantum revolution initiated by Max Planck's discovery of quantized energy was the catalyst for a series of breakthroughs that have forever altered our understanding of the universe. From Planck's constant to the uncertainty principle quantum mechanics has redefined not only our knowledge of the micro-world, but also our approach to science, technology, and philosophy. As quantum theory continues to evolve, it promises even more transformative insights and applications in the future. The journey through quantum mechanics has reshaped the landscape of physics and extended its influence into numerous other fields, from technology to philosophy. At the core of the quantum revolution were key insights, the most fundamental being the discovery of Planck's constant a concept that would lay the groundwork for the modern understanding of the microscopic universe. The idea that energy is not continuous but instead exists in discrete packets, or quanta, was revolutionary. Planck's work disrupted classical ideas and opened the door to a new way of thinking about nature. It marked the beginning of an era where the laws of classical mechanics were no longer sufficient to describe the behavior of matter at the atomic and subatomic level. Following Planck's pioneering work, Albert Einstein, took the next crucial step in applying quantization to the nature of light. Einstein's explanation of the photoelectric effect in 1905 was instrumental in demonstrating that light is not just a continuous wave, but also a particle, a quantum entity known as a photon. This discovery was critical because it challenged the classical wave theory of light and laid the foundation for the concept of wave-particle duality The dual nature of light, where it can exhibit properties of both particles and waves, became one of the central principles of quantum theory. Einstein's work helped cement the idea that the fundamental building blocks of nature are not as continuous as classical physics suggested, but are instead governed by quantum rules. Simultaneously, Niels Bohr, revolutionized our understanding of atomic structure by applying Planck's quantization concept to the electron orbits within atoms. In his **Bohr model of the atom ***, Bohr proposed that electrons move in discrete orbits around the nucleus and can only occupy certain allowed energy levels. This model successfully explained the spectral lines of hydrogen, showing that energy is absorbed or emitted when an electron transitions between these fixed energy states. Though later superseded by more complex quantum models, Bohr's work was groundbreaking in showing how quantum principles could explain the behavior of atoms, something classical mechanics had failed to do. The next leap forward came with Werner Heisenberg and his formulation of the uncertainty principle which introduced the radical idea that the act of measurement itself affects the system being measured. Heisenberg's principle posited that it is impossible to precisely measure both the position and momentum of a particle at the same time, a limitation inherent to nature itself, not just due to the imperfections in measurement tools. This shattered the deterministic view of the universe, where precise measurements and predictions were once thought to be possible. Instead, Heisenberg's uncertainty principle demonstrated that the universe at the microscopic level is governed by probability, not certainty, adding an element of randomness and unpredictability to physical laws. As quantum theory developed, it began to challenge not only the foundations of physics, but also the philosophy of science, ***. The probabilistic nature of quantum mechanics led to a fundamental rethinking of the nature of reality. If particles do not have definite properties until they are observed, then what is the nature of reality itself? This led to the development of several philosophical interpretations of quantum mechanics, such as the Copenhagen interpretation which held that the wave function, a mathematical description of a particle's possible states, collapses into a single reality upon measurement. The uncertainty principle and wave-particle duality raised profound questions about determinism, free will, and the role of the observer in shaping the physical world. These questions have influenced not just physics, but also philosophy, psychology, and the study of consciousness, where quantum ideas have even been proposed as key to understanding the mind. The quantum revolution did not remain confined to theoretical physics. It sparked a wave of technological innovation, that continues to influence our daily lives. One of the most direct applications of quantum mechanics has been in the development of semiconductors, which are the foundation of modern electronics. The invention of the transistor in the 1940 seconds, which relies on quantum principles, revolutionized computing, communications, and countless other industries. The quantum principles of superposition, and entanglement, are now being harnessed in the emerging field of quantum computing, which promises to exponentially increase computational power by solving problems that are intractable for classical computers. Quantum computing has the potential to revolutionize fields such as cryptography, optimization, artificial intelligence, and material science, leading to breakthroughs in everything from secure communications to new drugs and materials. The impact of quantum mechanics is also felt in more familiar technologies like lasers, which rely on the quantum behavior of atoms to produce coherent light. Lasers are used in a multitude of applications, from barcode scanners to medical devices like laser surgery equipment, to telecommunication systems that carry vast amounts of data across the globe. Similarly, Quantum principles are employed in the development of MRI machines, which allow doctors to peer inside the human body with incredible precision, and in GPS technology, which depends on the incredibly precise measurement of time provided by atomic clocks, another quantum-based technology. Quantum mechanics has also extended its reach to philosophy, particularly through its challenge to the classical view of an objective deterministic reality. Classical physics was grounded in the assumption that the universe was like a giant clock, governed by immutable laws that could be understood and predicted with sufficient information. Quantum mechanics, by introducing probabilistic elements into the equation, fundamentally challenged this view. The idea that particles exist in a state of superposition, where they can simultaneously occupy multiple states, raises the question: is reality itself a construct of our observations, or is there an objective reality independent of us? The philosophical implications of quantum theory have sparked debates about the nature of existence, consciousness, and the limits of human knowledge. These debates continue to shape not only science, but also the broader intellectual landscape. In summary, the quantum revolution, initiated by Planck's constant and developed by brilliant minds like Einstein, Bohr, Heisenberg, and Schrödinger, has fundamentally transformed our understanding of the universe. The ideas of quantization, wave particle, duality and uncertainty have not only revolutionized physics, but have also led to technological innovations that power modern society. Moreover, these advancements have sparked a deep philosophical inquiry into the nature of reality and our place within it. Quantum mechanics remains one of the most profound and successful theories in science, and its influence will undoubtedly continue to shape both our understanding of the universe and the technologies that define our future. The discovery of Planck's constant in the early 20th century marked the beginning of a profound shift in how we understand the universe. Max Planck's insight into the quantization of energy was the spark that ignited the quantum revolution, reshaping everything from the foundations of physics to the technologies that power our modern world. The quantum revolution also laid the groundwork for new philosophical inquiries into the nature of reality itself, challenging long-held assumptions about determinism, observation, and the limits of human knowledge. Planck's constant, which defines the relationship between the frequency of radiation and its energy, was the first glimpse into the quantization of nature, the idea that energy, light, and matter are not continuous, but exist in discrete packets or quanta. This fundamental idea was a direct departure from classical physics, which had assumed that energy could be freely divided into infinite, smaller parts. Planck's theory broke this notion and introduced a world governed by discrete, indivisible units. His work was crucial in explaining the behavior of black-body radiation, an anomaly that classical physics could not account for. It set the stage for quantum mechanics by introducing the concept that energy could only be emitted or absorbed in fixed amounts, laying the foundation for the development of the quantum theory. One of the next monumental steps in the quantum revolution came with Einstein's explanation of the photoelectric effect, which used Planck's quantization concept to show that light, traditionally thought to be purely a wave, also behaves like a particle. This wave particle duality became one of the defining principles of quantum mechanics. Einstein's work demonstrated that light is composed of particles called asterisk asterisk, photons asterisk asterisk, each with a specific energy related to its frequency. This finding not only helped to explain the photoelectric effect, but also provided experimental evidence that energy is indeed quantized, further solidifying Planck's groundbreaking discovery. The photoelectric effect became a pivotal moment in the acceptance of quantum mechanics, as it was one of the first experiments to provide empirical support for the theory that energy was not continuous, but instead divided into discrete units. In tandem with Einstein's work, Niels Bohr introduced his model of the atom, which applied the principle of quantization to the orbits of electrons around the nucleus. Bohr's model was groundbreaking because it explained the discrete spectral lines emitted by atoms, something classical physics could not. According to Bohr, electrons could only occupy specific energy levels, and energy was emitted or absorbed when an electron jumped from one energy level to another. This marked the first step in understanding atomic structure through the lens of quantum mechanics. Bohr's model would eventually evolve into a more comprehensive understanding of atomic structure, but it was instrumental in demonstrating the power of quantum principles to explain phenomena that had previously been beyond the reach of classical theories. As quantum theory began to evolve, Werner Heisenberg introduced his uncertainty principle, in 1927. This principle stated that it is impossible to measure certain pairs of properties of a particle, such as position and momentum, with perfect precision at the same time. The uncertainty principle introduced an inherent probabilistic nature to quantum systems, meaning that, at the smallest scales, the outcomes of measurements could not be predicted with certainty but only in terms of probabilities. This stood in stark contrast to the deterministic worldview of classical physics, where every event was assumed to follow a set cause and effect. The uncertainty principle undermined the belief that the universe was entirely predictable and instead suggested that randomness was an intrinsic property of nature at the quantum level. It revolutionized our understanding of how we interact with the physical world, highlighting the limitations of human knowledge. The wave-particle duality and Heisenberg's uncertainty principle led to further developments, most notably in the work of Erwin Schrödinger, who formulated his wave equation to describe the behavior of quantum particles. Schrödinger's equation replaced the deterministic paths of classical mechanics with a wave function a mathematical description of a particle's probability distribution. Rather than a particle having a definite position and velocity, the wave function describes the probability of finding a particle at various locations in space. This was a radical departure from classical physics, where objects were thought to have definite, measurable properties. Schrödinger's approach provided a more complete framework for understanding quantum systems, allowing physicists to predict the behavior of particles in terms of probabilities rather than certainties. The implications of quantum mechanics extended far beyond atomic physics. Quantum theory led to the development of technologies that have fundamentally changed modern life. One of the most significant advancements was the invention of the transistor which forms the foundation of all modern electronics. The principles of quantum mechanics, particularly the behavior of semiconductors made the creation of transistors possible. Transistors are used in virtually every electronic device today, from smartphones to computers, revolutionizing industries and communications. Similarly, **lasers***, which rely on quantum principles such as **stimulated emission***, have become essential tools in fields ranging from medicine to telecommunications. The application of quantum mechanics, in the form of quantum technologies, has sparked a revolution in computing, where quantum computing promises to solve problems that are currently impossible for classical computers to address. The impact of quantum mechanics also sparked a profound philosophical shift. Classical physics operated under the assumption that the universe was deterministic and everything that happened had a specific cause. Quantum mechanics, with its inherent uncertainty and probability suggested that at the most fundamental level, nature was governed by randomness rather than certainty. This opened up new questions about the realities. Nature of reality, and the role of the observer in shaping the physical world. The Copenhagen interpretation of quantum mechanics, which posits that reality does not exist in a definite state until observed, has led to philosophical debates about whether the universe is objective or if it only takes on definite properties when observed. Quantum mechanics has not only changed our understanding of physical phenomena, but has also forced us to rethink the very nature of existence and the limits of human knowledge. In summary, the discoveries leading up to the full development of quantum mechanics, from Planck's constant to Einstein's work on the photoelectric effect, Bohr's atomic model, Heisenberg's uncertainty principle, Schrödinger's wave mechanics, and the philosophical implications of these ideas transformed not only the world of physics, but also the fabric of modern society. Quantum mechanics has led to revolutionary technological advancements and has prompted a deep philosophical inquiry into the nature of reality. It remains one of the most successful theories in science, providing the framework for understanding the universe at its most fundamental level, while continuing to inspire new technologies that shape the future of humanity. The discovery of Planck's constant in 1900 by Max Planck marked the beginning of a profound shift in physics. It initiated the quantum revolution a paradigm that forever changed our understanding of energy, matter, and the very nature of reality. Planck's introduction of quantized energy, where energy is released or absorbed in discrete packets rather than a continuous flow, laid the foundation for the birth of quantum mechanics. This concept dismantled the classical idea of a smooth, continuous world and introduced the notion that, at the atomic and subatomic levels, nature is fundamentally different, discrete, probabilistic, and unpredictable. This was the first step in unraveling the mysteries of the microscopic world and understanding phenomena that classical physics couldn't explain. Following Planck's revelation, Albert Einstein, expanded upon the concept of quantization through his explanation of the photoelectric effect, In 1905, Einstein demonstrated that light, traditionally seen as a continuous wave, also behaves like particles photons each with a specific amount of energy. This dual nature of light, acting as both waves and particles, was central to the development of wave-particle duality a key tenet of quantum mechanics. The photoelectric effect provided compelling evidence that light behaves in discrete packets of energy, offering a direct experimental confirmation of Planck's theory. Einstein's work was pivotal in establishing the quantum nature of light and in cementing the idea that energy, whether light or other forms, was quantized. Simultaneously, Niels Bohr developed the first quantum model of the atom which applied Planck's quantization idea to the behavior of electrons within atoms. Bohr's model explained the discrete energy levels of electrons and how atoms emitted or absorbed specific frequencies of light when electrons jumped between these levels. This theory solved the long-standing problem of atomic stability, why electrons didn't spiral into the nucleus, as classical physics predicted. While Bohr's model was later refined, it represented the first major success of quantum theory applied to atomic structure, and it sparked further investigation into the quantum nature of matter. As quantum theory continued to evolve, Werner Heisenberg introduced his uncertainty principle in 1927, which reshaped our understanding of the universe at the most fundamental level. The uncertainty principle asserts that it is impossible to know both the exact position and momentum of a particle at the same time. This principle was revolutionary because it introduced inherent randomness into the fabric of nature. Unlike classical physics, where the properties of objects could be precisely measured and predicted, quantum mechanics showed that, at microscopic scales, uncertainty and probability govern particle behavior. The uncertainty principle fundamentally altered the deterministic worldview, highlighting the limits of what could be known about the physical world. In 1926, Erwin Schrödinger developed wave mechanics another fundamental component of quantum theory. Schrödinger's wave equation described particles not as fixed points, but as probability waves. Extending Planck's and Bohr's ideas into a more comprehensive framework. Instead of treating particles as individual objects with definite positions, Schrödinger proposed that particles existed as a distribution of probabilities, where their locations could only be predicted with certain likelihoods. The wave function he introduced represented this probability, offering a mathematical model for understanding quantum systems. Schrödinger's wave mechanics provided a more complete picture of the quantum world, with applications that would eventually lead to the understanding of atomic and molecular structures. The concept of quantum entanglement emerged as another key breakthrough, particularly through the work of Einstein, Podolsky, and Rosen in 1935. Their EPR paradox challenged the completeness of quantum mechanics, suggesting that quantum theory could not account for the instantaneous interaction between distant particles. Despite Einstein's discomfort with the implications of quantum mechanics, experiments conducted decades later proved the reality of quantum entanglement. Entangled particles, regardless of the distance between them, could instantaneously affect one another's state, defying classical notions of locality, and raising fundamental questions about how information and causality work in the quantum world. These developments led to the practical application of quantum mechanics in fields such as semiconductors, and quantum computing, semiconductors, which are central to modern electronics, operate based on quantum principles that govern electron behavior in materials. The invention of the transistor which relies on quantum mechanics to control electrical currents, revolutionized computing and telecommunications, enabling the digital age. Similarly, lasers, which operate by amplifying light through quantum principles of stimulated emission, have applications ranging from medical treatments to telecommunications and even the entertainment industry. The profound shift that quantum mechanics brought to philosophy is perhaps one of its most unexpected consequences. Classical physics painted a picture of a deterministic universe, where the future could always be predicted based on the past. Quantum mechanics, with its probabilistic nature and emphasis on uncertainty, overturned this view. The implications of observation, in quantum mechanics specifically, how the act of measurement affects the state of a system, led to debates about the role of the observer in shaping reality itself. Some interpretations, such as the Copenhagen interpretation, suggested that reality only comes into existence when observed, while others, like the many worlds interpretation propose that all possible outcomes occur in parallel universes. These philosophical quandaries continue to shape not just physics, but broader intellectual and metaphysical discussions. In conclusion, quantum mechanics fundamentally changed the course of science, technology, and philosophy. Starting with Planck's constant which introduced the quantization of energy, and continuing with Einstein's light quanta, Bohr's atomic model, Heisenberg's uncertainty principle, Schrödinger's wave mechanics, and the philosophical implications of quantum entanglement, quantum mechanics has redefined our understanding of the universe. It has transformed technology, led to groundbreaking innovations in electronics and computing, and forced us to rethink the very nature of reality. The quantum revolution, born of Planck's insight, has shaped not only the future of science, but the way we perceive the world around us.